Here in chapter one, and also in this book, we do go sort of, we start with the atom. So we start with electrons, like I said. We'll hit electron configuration in the next chapter, the atom in this chapter. Then we'll kind of go and do some other things. Then we'll swing back and kind of do some nomenclature and naming and bonding and stuff like that. So we jump around a little bit in this chapter, and we kind of go back and forth to some chapters. And the reason for that is the way they set up this class in the labs and stuff like that. So we do sort of bounce around from sort of chapter to chapter as we go through it. But again, the way this book is set up, it is sort of that atoms first. So let's talk a little bit about this here. So chemistry, right? The main thing about chemistry is the understanding of sort of what happens on sort of the big level and related to what's happening on the microscopic world. So when we look at these things, they can be very, very different. For example, you could do a reaction, for example, in like a beaker, and this reaction is pretty much looks to you like it's done. It's changed color, it went to red or whatever, say it may be. And it doesn't really look like, for example, anything is happening anymore. Everything is done. But there are certain types of reactions, and especially ones that you'll talk about, say in 200B. If you were to sort of super zoom, for example, and you looked at a reaction, there could be with this type of reaction, which is sometimes referred to as a reversible reaction, which means there is sort of a forward direction where we got our reactants, which are over here, going to our products, which are over here. And at some point, what will happen in this reaction is the products will kind of recombine and head back in the other way. And this is what is referred to as a reverse direction for that particular reaction. So although when you look at like the beaker and it just looks like everything's done, there is a lot of activity basically happening in this reaction, sort of on the molecular level, going back and forth, up and back, and stuff like that. That you may think like nothing's happening, but just keep that say red color, for example. There's a lot of back and forth sort of happening. So we do try to think about what is happening on the molecular level to explain what we do see sort of on the big level. And a lot of what we deal with in chemistry does deal with basically the idea of matter. And matter is basically anything that has mass and occupies space. And a lot of what we deal with in chemistry is the different states of matter as something goes from, say, one state of matter to the next. So, for example, we do have the solid state of matter. And in the solid state of matter, typically things are packed in there pretty tight to one another. There's not a lot of room for movement. There's not a lot of energy, which is why things sort of just kind of lock into place. And things are, as we kind of figure them, as solid. There's also the liquid state of matter, where we still have things relatively close to one another. But in this state of matter, we do have a lot more energy than you say do in the solid state of matter. So there's a lot more movement that's actually happening. And that's why we think of liquids as being fluid, because they have a lot more energy. So those guys could actually slide past each other. And that creates that more fluid sort of environment that we see in the liquid state. And there's also the state of matter, which is gas. And the gas state of matter, pretty much everybody has broken apart from one another. There are flying around and moving around. And as we'll talk about when we get into sort of the gas chapter, those collisions that occur as they are flying around and moving around in that container is what we associate pressure with when we think about gases. So a lot of what we see in chemistry is this idea of matter and how matter changes. And one very common way that matter changes is it changes states, going from solid to liquid, liquid to solid, and all that kind of stuff. As we do these transitions, as we go from solid to liquid, that is the process of, what is that? When we go from solid to liquid, the process of Melting, yeah. Like we take an ice cube out, right? As we go from liquid to solid, that's the process of freezing, right? We go from liquid to gas, that's the process of evaporation or vaporization. Going from gas to liquid, that is the process of condensation. We could also go from solid, skipping the liquid state, right, and hitting gas, and that is the process of sublimation, like a little dry ice action. We also head this way, gas back to solid, skipping the liquid phase. That is the process of deposition, like you're depositing something on something. So a very common thing that we look at in chemistry is as things change, as things go through evaporation, melting, freezing, condensation, deposition, what is happening in those situations. As we look at a process, for example, does the process of melting and freezing, does it happen at a different temperature or the same temperature? It actually happens at the same temperature is actually where this occurs. So this actually occurs at the same temperature. For example, the normal freezing point or melting point of a substance, for example, water is 0 degrees Celsius is where that occurs. What happens at exactly 0 degrees Celsius is this. It depends on what you're doing in terms of energy, which is also a really important component of what we look at in chemistry. If you continue to supply heat as you go from solid, it will go through to the liquid phase. So if you think about the ice cube, if you take an ice cube and you apply more heat to it, like heat it up, that ice cube is going to continue to melt, right? And if you remove energy at, say, 0 degrees, that thing will go from liquid as they have a little bit of energy moving around. And as you remove the energy, everybody's going to slow down and they're not going to be able to kind of move past each other and they're going to lock themselves into the solid state. And so energy is a really big component. Same thing here with evaporating and condensation occurs also at the same temperature. That's the normal boiling point of a substance. And the same thing happens at, say, for example, water, 100 degrees Celsius is the normal boiling point of water. And at 100 degrees Celsius, it does depend on what you're doing in terms of energy as to which way you will go. When you're exactly at those temperatures, by the way, you actually have both phases happening at the same time. So when you're at 0 degrees Celsius for, say, water, you'll have some liquid water, but you have a little bit of ice crystals happening. It's not really until you get a little bit above 0 degrees Celsius that you kind of transition fully into water or liquid water, until you get a little bit below 0 degrees Celsius that you transition kind of fully into ice or sort of the solid. So energy is also a really major part of what we deal with in chemistry. Side note, not too much in this class because they took energy out of this class and put it in 200B. So when you get to 200B, you'll do the energy chapter, which we actually don't do anymore in here. But along the way, we will talk about energy in certain places because your textbook assumes that you probably did that chapter that comes early on in the textbook. So even though we don't do it anymore in here. So when we go from solid to liquid to gas, does energy need to be put in or taken out to do those processes? What do you think? Energy needs to be put in to do so, right? So if you take the ice cube example, when you take an ice cube out, it picks up all the energy from the surrounding air, right? And it starts to melt. You take some water and you put it up there on the stove to boil it to make some pasta. You're putting energy in, it starts to boil, right? So these are all processes where energy is absorbed. And in chemistry, when energy is absorbed, that is referred to as being endothermic. And in terms of values, as we'll talk a little bit about as we go through some different chapters, typically if you're given an energy value that's a positive value, that usually refers to a endothermic type process. So energy is being absorbed. Opposite is true. As you go from gas to liquid to solid, the idea there is in the gas state, everything's flying around really fast with a lot of energy. You have to remove that energy. And what's going to happen is as they are flying around, they lose that energy, they hit each other, they no longer have enough energy to escape each other, and they drop into the liquid phase. And if you continue to remove that energy, they're just going to kind of slow down and lock into place into the solid phase that's going to happen. So as you go from gas to liquid to solid in terms of energy, energy is usually released. And that in chemistry is what is referred to as being exothermic, when energy is released. And usually, if you have some type of energy value given to you, or you calculate the energy, that is usually a negative type of number that occurs. So energy is a really important sort of aspect of what we deal with in chemistry. A lot of things we do look at energy. It's everything from energy or absorbed or given off in chemical reactions. Also, perhaps making and breaking bonds involves energy. So energy is really a very key component in terms of chemistry as well. By the way, when we talk about energy or we talk about heat, heat goes from cool to hot or hot to cold. Heat travels which way? Heat travels from hot to cold. That is why when you take your ice cube out, it is colder than the air outside. That is why all the air outside is enough energy to start to melt it, because it's hotter outside than the ice cube's temperature. Heat travels into the ice cube and starts to melt it. That is also why when you take liquid water and you put it in the freezer, your freezer temperature is colder, right, than the liquid water that's room temperature that you just put in there. So the heat travels out from the liquid water to the freezer, right? And that causes the liquid water to lose energy and come into the solid stage, and you make ice cube. So heat and energy always flows from hot to cold. Any questions on any of that? Now, other things obviously that we talk about in chemistry, which is really important, the atom is really the sort of smallest unit of any element that's there. As we'll talk about, it's made up of protons, neutrons, and electrons. But the atom is the basic sort of representation of any element there, say on the periodic table. A molecule is the combination of two or more atoms that are bound together, however they are bound together. So this does bring us sort of a little talk about some differences between sort of what a molecule is and, say, for example, what a compound is and what an element is. And to just sort of preview that there, these are, for example, an element is really as far back as you could go. And again, they're represented by an atom is a simple representation of them. Everybody on the periodic table, those are all the elements, those are all the symbols for the elements. But there are certain elements that come as diatomic molecules. And diatomic molecules means pretty much what the name sounds like. Di means two, atomic means atoms. So they are two atoms that are together. For example, hydrogen, the way it naturally comes is as a two, oxygen, nitrogen, fluorine, chlorine, bromine, iodide. These guys are all elements, and this is naturally how they come. So if you have a hydrogen, comes two of them together. If you have an oxygen, two of them together. You have a nitrogen, two of them together. And these are all considered elements. Pretty much all the other elements comes as monoatomic, which means they come as ones. So they all come as one, as they naturally are uncombined. Now, these are all elements. They're also all considered molecules, and they're diatomic molecules, each of these guys. And that's because they're made up of two atoms of each of these elements. So We have 1 and 2 atoms of this guy, 1 and 2 atoms of this guy, 1 and 2 atoms of this guy. So that is why they are also considered a molecule. Now, when we talk about diatomic molecules, sometimes people think that it does have to be two of the same, and it doesn't. It just means that there's simply two things. So if you had something like carbon monoxide, for example, CO, that is also a diatomic molecule because there's an atom of carbon and there's an atom of oxygen together, basically. Um, now, molecules and the word compound, which we'll see probably a little bit later, but since we're talking a little bit about it here, we'll just kind of jump into it. A compound is the combination of two or more atoms of different elements. And that is the distinction between, say, a compound and a molecule, which is just really the combo of two or more atoms. So the combination of two or more atoms is pretty much all you need for something to be considered a molecule. And those two or more atoms could be two of the same or two different ones. That's basically, it's like a general definition of something. It's just like generally all you need to meet the molecule threshold is I have two atoms or more together. That's basically all you need. Now, in order for it to be a compound, it does need to be two or more atoms of different elements. So for example, if we did CO or H2O, that is a combination of a carbon element atom and an oxygen atom. That is a compound. That is also a molecule because it has two or more atoms together. CO is not an element, right? Because it's made up of two different elements. So H2O, combination of two or more atoms, which means that's a molecule. Combination of two or more elements as well. That is a compound. H2O is not an element. So molecules and elements, you can, again, think of molecules as just like a general definition. All you need is two or more. Could be the same, could be different. But in order for something to be considered a compound, it does need to be two or more different elements involved. Any questions? So other things that we'll talk about along the way, we can take compounds and break them apart by some type of electrical means or chemical means. And you could break them apart into elements, but that again is pretty much as far back as you can go. So you could take something, for example, like water, and simply just run an electrical current over it. 9-volt battery will do. And you could break it apart into hydrogen gas and oxygen gas. That is a chemical sort of change that occurs. And in a chemical change, basically what you start with and what you end with are fundamentally different things. And you can't get those things back by any type of physical means. Now, that is a different process than when I boil water, right? When I boil water to make pasta, right? And I get steam, that steam is still H2O, right? It's still water. We didn't break it apart or anything like that. That's a physical type change as it goes from liquid to gas, which is a change of state is physical. Something like this, where you might take water and run electrical current over it to produce hydrogen gas and oxygen gas, is more of a chemical change. We obviously use subscripts as well when we do write formulas. And when we write formulas, the subscript, which is the number on the bottom, is always goes to the guy to the left. So that means we have two hydrogen atoms here when we talk about water. If there is no number pretty much written in chemistry, that usually means one. And we typically don't write one for numbers and stuff like that. So that also would go to the right here. This would mean there is one carbon and one oxygen. And obviously each of these guys would have two of the respective elements in each of these cases. So that's very common how we obviously write formulas. As I mentioned before, a chemical reaction is oftentimes studied in chemistry, and clearly in a chemical reaction, that is, again, pretty much a chemical change. And that means what you start with and what you end up with, again, are two fundamentally different things. There is a very big difference between water, liquid water, and hydrogen gas and oxygen gas. And again, that is definitely a chemical change. The only way you can get the water back is to do another chemical change or chemical reaction to produce water. Um, that is also why when we boil water, as I mentioned before, and we create steam, that is a physical change, because what you could do with the steam is cool it down and you could get the liquid water back, and that would be condensation occurring. Kind of like when you take a shower and it gets really steamy, but it hits the really cold mirror and you got water on your mirror, right? That steam that goes there, hits the cold water, will transfer its energy over there to the cold sort of mirror, and it will go through condensation, right, and create that sort of liquid water back. So a lot of what we do in sort of science is we do look at sort of the scientific method, and the scientific method is really a plan or a pathway that's taken by a lot of people that obviously study science. And it really all starts with a lot of times an observation. And sometimes you take an observation, and that does lead to some type of questions. And those questions are usually tried to answer by coming up with a hypothesis. And a hypothesis, or a good hypothesis, is really something that is testable. So, for example, usually in science is some type of thing that you could do some type of experiment to try to investigate the observation that you made. So that usually will lead to some type of experiments. And it's really at this point that you get into sometimes a vicious loop of, oh, I just made more observations. Maybe I have to readjust my hypothesis and maybe do some more experimentation. So the scientific method is really all about that. It's about sort of coming up with a tentative explanation of what you're observing, doing some type of experimentation either to sort of prove or disprove your hypothesis, and then perhaps leads to more experimentation. The ideally and sort of the ultimate goal here is to maybe at some point you hit a theory, or maybe you hit some type of law that will come out of sort of that investigation. And there's sort of a difference between, say, a theory or a law in terms of, their meaning. For example, as we'll talk about a little bit throughout some different chapters, theories are things you could think of as it is thought to be true. It happens very often in this sort of fashion. But if theory is not necessarily set in stone, it can be later proven maybe not to be correct in all aspects of it, or maybe it's thought to be correct in only some parts, but other parts are not right, and stuff like that. So, for example, when we talk about sort of a theory, there is the Bohr theory of the hydrogen atom, and Bohr's theory works really well for hydrogen, but as soon as you hit anybody with more than one electron, it doesn't hold up so well. Dalton's atomic theory, which we'll talk about in this chapter, works really well, but there are parts of it that was later shown not to be so correct in all aspects of it. So a theory is something that can be modified, can be thought of as maybe being revisited. A law, on the other hand, is something that always happens the same way, no matter what the situation. So the law of conservation of mass, whatever mass you start with, you will end with. And that's, for example, in a chemical reaction, why when we balance equations, because if we start with 6 carbons to start with, we'll end up with 6 carbons on the other side. But they may be in different things, but we'll still have the same number of carbons, for example, what we start with and what we end with. And because carbon, for example, is 12 grams or so, we'll have the same mass on each side of the reaction as well. Conservation of energy, we don't create nor destroy energy, but energy is transformed from one place to the next. So the idea of that is as somebody sort of loses energy, somebody else gains that energy. So like when I bang on the counter, energy is transferred to the counter, right? It just doesn't disappear and stuff like that. So there's always sort of that process. Here's sort of a schematic of that. Like I said, it can be sort of a vicious circle, but hopefully at least is some type of theory or law, which really does sort of summarize what happens. And as I mentioned before, a hypothesis is again a good one, a testable sort of explanation of what you're observing. All right, so I think that's a good place to lay it up.